Okay, I just cleared the blackboard there, but I want to go over. All right, so I still got a minute here. I'll chill a bit as I look up some logarithmic models and then work on the properties of logarithms a bit. All right, so is the volume working over here? Yeah, that's going good. Hey. All right, so short recap. We invented two new classes of functions. Hey, Josh. So these two new classes of functions are exponentials and logarithms. I showed three types of I showed two types of exponentials: growth and decay. And then I kind of showed the interest formula in its large sense. What I want to do is look at particular models for right now, and then we'll get into the actual algebra that we can use with these types of functions. I forgot at the very end when I said that the amount was equal to the principal of the 1 plus n r over n and t, that this whole thing approached e to the rt. And so we actually write our interest formula if it's compounded continuously as PERT, the principal times the exponential base to the RT. And that most modern interests are done compounded continuously. I guess there's still some banks that do quarterly or monthly. I think my credit union does a monthly compounding. But most financial services tend to use the principal is the exponential RT. What I want to look at is logarithm models, how the function of a logarithm itself tends to work. And the best model for a logarithm really is in scales and scaling factors. Human beings tend to have logarithmic senses. And I'm going to think of this as what a exponential function looks like in reverse, because that's what logarithms happen. And in astronomy, we use lots of log scales. And in a lot of biological sciences, log scales come up. But think of an eye, or an ear, or any nerve ending. And the exterior nerve ending has sensors. And all of these sensors connect into trunks on the nerves. And those trunks connect into other trunks, which eventually make your way back to your brain. And so you have these signals that come out from these branches upon branches upon branches. And if one of these is firing, you have a very weak signal. If one branch is firing, you have a slightly stronger signal. If all branches are firing, you have a much stronger signal. But it's not linear. It's exponential. The number of things at the end of these has grown exponentially. But we tend not to have our senses work exponentially. We tend to feel them linearly. When we make pain scales or light scales, or when we look at sensitivity of things, we tend to think about them in terms of a linear measurement. And so a lot of times we will have functions that are logarithmic. They look at a scale that works in logarithms because our input has many things on the end, but by the time it reaches here, we have one signal, and it's a multiplying factor each time it comes through a branch. And so a good example of that, I'll look at sound for one, which we tend to measure in a thing called decibels. And the power intensity of sound that the lowest the human ear can hear is 10 to the negative 12th watts, I believe. Make sure I get it right. 10 to the negative 12th watts. Let me make sure. Got like 15 piles of notes here. Everyone's back in. Good. Sounds a little odd tonight. I think so I'm going to try to talk louder. And let me get my decibel equation here. Yeah, so we tend to look at decibels as a measure that we'll have it as some function d. And the base, or the lowest sound a human being can hear, is 10 to the negative 12th, I think. Let's see here. Where is my I not here? I apologize. I walked out. Threshold of hearing. There it is. 10 to the negative 12th watts per meter squared. Yeah, 10 to the negative 12th watts per meter squared. Sorry. 10 to the negative 12th watts per meter squared. Which, that's the lowest sound you can hear. And so what happens is something beats the air. That's what creates it, and a sound wave goes out. And that sound wave has power that's 10 to the negative 12th watts per square meter. I think your book uses per square centimeter, which is 10 to the negative 16th. This number changes if you measure it per square meter. But the power intensity has a measurement. And it's how much air moves by your eardrum. Well, if we were to measure things to 10 to the negative 12th is the lowest your ear can hear, well then what happens when your ear begins to hurt? Or things begin to be painful. And so we had to have a scale that worked with this, and a scale of sounds. And so the decibel scale took this nerve ending thing we heard and the range of sound intensities that we could hear, and it turned it into a scale. And it did this this is showing, by saying, hey, we're going to make something that counts in tens, and we're going to use log base 10. And it's going to be the power of what you hear divided by the lowest thing you can hear. And this is an important thing that's going to come out in these functions, and I didn't emphasize it as much in the exponential functions as I should here. But anything that goes into a log or an exponential function should be unitless. Because this function has everything up in the exponents or the powers. The unit needs to go away. And so if I have something that I'm measuring in watts per meter squared divided by something that I'm measuring in watts per meter squared, they're going to cancel. Just like when I had in my exponent, I'll put my exponent up here in cyan. And I had time divided by my half-life. Both of these in days, the days canceled. I can't put things into these functions that have a unit. And so you're going to see a lot of ratios of things coming through here. It's one of those things that I do so often I forget to mention it, but it's actually extremely important. I remember in general relativity I was working on a function, very, very complex mathematical function, and an exponent was the answer. But I forgot to carry a term in one of the derivatives, and it gave me something with units, and I didn't see it. And I remember my friend Charles is just like, you can't have units in an exponential. You messed that up. And it's one of those things that we tend to look for. These functions, logs and exponentials, the units have to cancel. Whatever the units are of what I'm putting into it, then I have to divide by something with the same units. And that thing we divide by in decibels tends to be the threshold or the base unit. And so I actually need to change this to an I. And so we can measure a sound scale based off of the strength of the power of things we hear. And so if the quietest thing a person can hear is 10 to the negative 12th watts per meter, then what we want to do is we want to look at some different sounds and what those sounds look like. So let me see here. I had a nice one here. I had a jet engine at one point, but through. It's not the one I want. 2 seconds here. Right now I have a 40 decibel thing, but I want to look at jet engine. Sorry, I'm grabbing another textbook here. Hold on 2 seconds. No, my textbooks are on my computer. And of course logging in. Everything in decibels. I want the watts per meter squared, which I had in my blue notebook, but I cannot see where I set that down. All I have is stuff with earthquakes in it, and this is the one I wanted to show. Okay. Well, okay. 2 seconds here. I'll use the book example. So the human ear starts to hurt. I have what decibels are for a jet engine in decibels. So the ear starts pain at an intensity of 10 to the 0 watts per meter squared, or 1 watt per meter squared. Should I have that number right? All right, so we can find this measure in decibels. So I want my decibels of 10 watts per meter squared as a function. It's going to be 10 times the log base 10 of, well, I'm putting in 10 to the 0 watts per meter squared, and I'm dividing it by 10 to the negative 12th watts per meter squared. So this is how a log function works. And, well, I'll show you what happens to the calculation. This is fairly nice for us, as we're going to look at some properties of logs. So I have the same base with different powers, so that becomes 10 to the 12th, the watts per meter squared. All right, 10 to the 0 divided by 10 to the negative 12th. I subtract my exponents. That gives me 10 to the 12th. Well, my rule is log base 10, I'm going to the 10th power. Remember I said the magic sauce was log base to the x gives me x. Common log is to base 10. So I'm going to mentally think these cancel each other out. And that gives me 10 times 12, or 120 decibels. And so instead of saying that when I try to hear things, and the lowest sound I can hear is 10 to the negative 12 watts, what we tend to talk about that lower threshold being is that 0 decibels. And then when I think of a sound that starts to hurt, that's 120 decibels. And so we made this scale now that works on numbers where the smallest number is 10 to the negative 12 watts per meter squared. And we move up to something that's 10 to the 0 watts per meter squared. And so that's, if we were to write that in decimal places, that's, 0.0, there's 11 zeros here, all the way to something that has 1.0. And so there's many powers of 10s in there. It becomes a very hard series of numbers to work with. But a log scale puts those just the numbers 0 through 120. And the difference between 0 and 1 is multiplying by 10. The difference between 1 and 2 is multiplying by 10 more. And the difference between 2 and 3 is multiplying by 10 more. That's how log scales work. Is every time you go up a number, it's 10 times more powerful. And for the reason that I explained, that nerves tend to branch out and the signals tend to be multiples as your body gets more sensory input in, human beings tend to think in log scales. And so log scales are very useful. You will see log scales happen within hearing. We have log scales within sight. We have log scales within pain scales, and the ability to use logarithms. Most of the time, it's a log base 10, and the thing we're measuring is something to the power of 10. This is why the log base 10 is useful, how we do our decimal places. Well, there's a similar scale that we use in chemistry, which is the pH scale. And the pH scale works with how many hydronium ions are in a solution. And what we want to do is we want to count the molarity of hydronium. And so what we do in the pH scale, and this is per hydronium ion, that's what it means, is we take the negative of the log of how many hydronium ions are in there. And so we can count the molarity of them. And so it's kind of like the percentage of them, or how much per liter comparatively. And so we end up with really, really, really small numbers on this, the molarity of it. Typical molarity counts, we can look at like 10 to the negative 4.7 would be a molarity count, which is on that level of a percentage. And so the amount of these ions that are able to interact in a solution determines its acidity. And so pH is a way of doing that. Well, the scale of pH goes from 1 to 14, with 7 being completely neutral. The base acidic reaction is balanced, which is where pure water is. Acidic things are this way, and basic things are this way. And basic things are things that give us like a soapy feel. Bases react with acids, but it's a hard thing to measure, and measuring in these numbers, which have very large sets of decimals. So what we can do is we can look at the hydronium ion concentration, and we can say, okay, well, let's look at what the hydronium ion concentration is. So this is rainwater in Europe. Has a hydronium concentration of an order of magnitude of 10 to the negative 4.7. So it's saying the concentration of hydronium ions in rainwater is 10 to the negative 4.7. Well, that's a hard number for us to deal with. So we put it into the pH scale, right? We put it into the test kit we use with the swimming pool or with the fish pond, right? We have the little test kits that measure the pH level. So let's put this number in and see what happens with the pH. So pH is the negative log of this hydronium number, so 10 to the negative 4.7. Well, notice that a log is base 10. And so that magic sauce I said that anything with the same base will give me x coming back out. So log base 10, because this is the common log in base 10, the 10s cancel, and that gives me negative times negative 4.7. And this has a pH of 4.7. And it's acidic. And so what we end up doing again is taking a series of numbers that would range from 10 to the negative 14th to 10 to the negative 1, or roughly 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. From there to there, that's the range of numbers we could have. We could have every value filled in there, and we put it on a scale between 1 and 14. That's the purpose of logs, is taking this complex domain of things that has a large stepping value and condensing it onto a domain that's easier for us to handle or carry within our comparisons as we move across. So this is the main use of how we use logarithmic models. And earthquakes, the Richter scale, the tornado scales, all these scales we have that kind of go 1, 2, 3, 4, 5. Usually each level on that scale is 10 times more powerful because of the logarithms that they're using in the background. But it's easy for us to compare these whole numbers. Yes, Emily, the Richter scale is very like, sorry, you didn't see your comment there. Yes, the Richter scale is like that. And it's because the things we are measuring are so large, carry so much numbers in it, it's easier for us as human beings to talk in 1, 2, 3, 4s. And so all of our scales work this way, and they all use some type of logarithmic measure. In fact, the Richter scale, if I remember correctly, is log the intensity, the power intensity, over what an initial power intensity. And I think that one is, what is their isomnot? I think the isomnot they look at is 1 joule, because you can measure it in joules, and I've seen it measured in watts per meter squared also. I'll have to look coming through, but it is very similar to how we do decibels. In fact, physically the system, right, a sound wave is some disturbance in the air that moves sound waves out through it, and an earthquake is some disturbance in the earth that moves vibrational waves through the earth. And so it's a similar idea on how they measure the intensity. And so these are the things that we model with logarithms and exponents. I think decay and growth happen a lot, and for logarithms it's scales. Most of the time you see a logarithm, you will be looking at a scale. All right, so those are our two big models and the big types of problems we'll come up with. Well, these are our things, and we're going to play with them more and more in the homework. It's how we want to play with these to help make the models do things, but we're gonna have to do some algebra with these functions. And I really want to appreciate that this is a collection of infinite functions that we can do a lot of things with. It's really hard at this level to appreciate how much this stuff is useful until you start seeing it over and over and over again. So what I'm going to do here is I'm going to answer the calculator problem we have and use that as an introduction to the algebra that we're going to have to deal with. And having a way of solving some, and then we're going to look at how we can solve different exponentials and different logarithms. So I'm going to start with the calculator problem, and then I'm going to do work with an exponential problem, and that should set us up for everything we need for the algebras here. What I'm going to do here is I'm going to write all of the rules that we're stuck with, and I'm going to keep coming back to these rules. So I'm going to go back to doing this. I'll put my exponentials over here. And the rules that I have is b to the 0 equals 1. Oh, and I'll put an exponential function over here as b to the x is its basic form. B to the 1 equals 1. I'll even put this one here because we might need that at some point. If I multiply two exponentials together, I add their exponents. If I divide two exponentials, I subtract their exponents. And if I take a power to a power, take an exponent to a power, if I take the whole function to a power, I multiply the exponents. Alright, I think that covers the base of the main ones. And then I'll look at my logarithms. And so I have a logarithm of some base of x. And then so what we're going to say is the log of any base 1 is equal to 0. Whoops. Fix me over here. That was my bad. That should be b, right? B to the first is b. B to the 0 is 1. The log of any base that spits back out the base spits 1. B 1 over b equals -1. Sorry, as I'm writing these rules down. This would be the moment in class when you would see my back as I try to write everything down and I mumble to myself, trying to pretend that I'm still communicating, where writing them down is the important part. You know it. You've seen me do it. So if I subtract two logarithms, I can combine their terms in the middle. And let me see if I can do this in a way that matches my input and output. Yeah. That power in here can come back out front. These are the main rules of logarithms, but the other nice thing hangs out in front, which is if I have some logarithm of a base and I take the base to a power, I get the power back because they're inverse functions, the magic sauce. And if I take a base to a power that is the logarithm, I get the component of the logarithm back out. This is how we get rid of these things. And so this is going to be the basis. We're going to need to build an algebra using this. We have rules of what happens when we add things, that we can condense them together. When we subtract things, we can condense them together. When I have a power, I can condense or manipulate them. And so these rules combine how we're going to combine our components. The things we always need the same are the bases. All right, so this is I'm going to start with our calculator problem to show you where we're going with using algebra for these things and how this can help us solve different things. And yeah. So I am going to calculator. Has two keys. ln and log. And so I have the log of e to the x and I have the log of 10 to the x. That's all I have. So what do I do when I want to find log base 2 of some number? Right? Unless it's a clear power of 2, I have to either make a table of all the powers of 2, right? So if this is log base 2 of 1, I know it was 2 to the 0, but if it was log base 2 of 3.146, well, 2 to what power gives me this, right? And so I can't remake a table. I need to use my tools. Old days, we'd go pull out a table and look it up. Now we have calculators, but our calculators do not have all of these properties in it. So we're going to look at what's going to be called changing the base. We'll change the base formula. This is useful because this will let you calculate anything on your calculator using those two keys. And I'll show it in two ways and we'll compare the answers to it. But also the manipulations we're going to do is going to show what we're going to have to do with all these rules. So let's say I have a log to a base that I don't know what it is. And I have x, and I want to find this answer, y. So I have a base that is not one of my calculator keys. So b is not e or 10, because I have the keys for e or 10. All right, so what I want to do is I want to find a way of solving this. So I'm going to write this in a way that will let me solve what I'm looking for. So I'm having log equals log b of x. So I am going to take both sides to this base. I want to do a mathematical trick here, right? Remember, in mathematics, whatever I do to one side, if I repeat it to the other, I maintain equality. And so if I have 2 equals x plus 1, I know x is 1, right? But I could do this. I could do 4 to the second power equals 4 to the x plus 1. I could take this entire left-hand side and make it the power to some base, arbitrary base. That's completely okay. This equality is going to stay the same. In fact, if I have b to the x equals b to the y, I know x and y equal each other. If I have some base to a power, and it's equal to the exact same base to a power, those powers have to equal. And so that's what I can do here. I can say 2 equals x plus 1. Well, that's the same as 4 squared equals 4x plus 1. Well, this might be a reversible process, and reversible processes are good. So here, I'm going to focus on this base, this thing that I do not know what it is. And so I'm going to take this side and this side to the base. So I'm going to say b to the y is equal to b to the log base b of x. Now, it's a valid mathematical trick. I've enforced a base, and the base I've enforced is the one I don't have a key for on my calculator. But if I come up here, notice a base to a log base b of x is just x. And so I've gotten rid of that from out there. I have gotten rid of the logarithm I don't have a key for. And these are mathematically correct. All right. Well, I do have a natural log key. So I'll take the natural log of this side, and I'll take the natural log of that side. That's fair, right? If I take the natural log of something on the left-hand side, it's got to equal the natural log of the same thing on the right-hand side, because the equal sign says they're the same. So I can drop both sides into these functions. Now notice I'm leading us to what we're going to be doing a lot of, is using these things as mathematical operators like we did before. So please bear with me and smile. I know this is new. Lots of smiles. All right, well, I have a rule here about powers. I'll scroll back up to it. That if I have something to the power, I can multiply the power out front. So I'm going to do that. I'm going to bring the y out front. Look, I have done something we couldn't do before. By inventing these logarithms to be the opposite of the exponents, I have been able to take my variable out of the power and bring it down into the equation. There. Look at this. With this y, right? Well, we forced the y up there, but we had nothing to bring it back down. Well, now we do with the natural log function. And I can pull it out front. After a lot of times, if you have variables stuck in the exponents, you take a log and they'll multiply back down. Well, y, I'll divide both sides by the natural log of b. And there's our answer. And this is called the change of base formula. There's my initial base, right? What I started with up here. My initial base is in the base of my new function. But notice I'm doing it in terms of what the calculator can do. And there's my initial x. It comes up here. Now this part right here, I could have done it this way. So I'm gonna switch over to Fire Engine Red. And I'm going to come to this step right here. I'm going to bring this step right back down. B to the y equals x. And you know what? I don't like the natural log key. I like the log key on my calculator. So I'm going to make this log of b to the y equals log of x. Because if the stuff on the left-hand side is equal to the stuff on the right-hand side, well, if I take the log of the left-hand side, I should get the log of the right-hand side. Because they're equal. So they'll do equal things. Well, my rule says I can pull the y out front. And I'll divide both sides by log b. And notice these are similar, but I'm using different keys on my calculator. So I'm going to do one here. And I'm going to go back to a problem that we had earlier where we had powers of 2. right? And so let's say I want to use log base 2, and I want to know what gives me 2 to what power is equal to 6. Right, the change of base formula says, hey, I can take ln of 6 and divide it by ln of 2. So I want to do that on my calculator right now. Ln of 6 divided by ln of 2. I get 2.584962,501. I like that. That's usable. All right, but let's say I use the other key. So let's say I'm using my log key. So log base 6 over log base 2. So where's the log key? Log 6 divided by log 2. My golly, I got the exact same answer. This change of base formula lets us use any logarithm base. We can get rid of it and we can use the one we have the tables for. Remember, there are an infinite amount of bases. Any number I can make a base to an exponential. I could have the base of 3.218 and to the xth. And so I would have to have a log for 3.128 to reverse it. And mathematicians could only publish so many tables to do this. And so they use these log rules to go, just use these two tables, log base 10 or log base e. And when calculators got invented, we're only going to give you two keys, log base 10 or log base e. And so the change of base formula is what we use. Now, in general, what it says is your answer is the log in the base that you want of the number that you started with to the log of the base that you want with the base that you started with, right? And the A is your option, right? And usually A is equal to E or 10 because those are the keys calculators have. Those are the common tables that everyone uses for these. So notice we have created a formula for ourselves. And this is probably one of the most useful things to come out of these early attempts at using exponential and logarithmic algebra, and how these rules come together, is that I can take whatever base I am given and I can make it work for the bases that I have. And notice these steps here use these rules. And these are the algebraic rules we're going to use and explore as we go through logarithms. I'm going to show you another one, and I'm going to have it work with phosphorus. And I'm going to do this phosphorus problem that we looked at again, and I'm going to solve in a different way for it. See if I have it here. Yep. There we go. Let's see. Or actually I'll go carbon dating. Let's go here. So carbon dating, right? Like speed dating for coal. No, that's not what carbon dating is. So carbon dating. So carbon has a radioactive half-life, and carbon decays. So the amount of stuff I have in carbon, that's an A. The amount of stuff I have in carbon is my initial amount actually, let's just, my handwriting This tablet is killing me. I said this earlier, I'll say it again. Carbon dating. So carbon has a half-life, and specifically carbon-14, of 5,730 years. All right, so what we're going to do is we're going to calculate carbon, but we're going to do it in terms of an E exponential. And this is something that's really common. I could right now write a half-life formula based off of the exponentials we did before, like this. Because I'm going to take 1/2 to the power of t divided by 5,730. What ends up happening in a lot of problems is that people use exponentials and to do all of these. That way they don't have to worry about different bases. So I'm going to do this as an exponential problem. And I'm going to show you again, I'm getting here, I'm trying to get all these rules of algebra into our models so that next lesson we'll explore a lot of the algebra techniques. So let's look at what it means for half-life in this model. I'm going to convert this model to my amount is equal to my initial amount of E to some K to the T. So I'm going to have a K constant that is my decay rate. Remember how I said earlier when I introduced exponential models that people will tend to use the e to the something and they'll let the k adjust it. I can choose the k in exactly the right way that it acts as if I'm doubling or halving with a particular half-life. And here's how we'll do it. So I want to know when a half-life is telling me that if I start with a sub naught, a is equal to 1/2 a sub naught. Right? When do I have half of my amount? So I'm going to put all of this in here. That gives me 1/2 a sub naught equals a sub naught e to the negative kt. Well, I'm going to divide both sides by a sub naught. So I get 1/2 equals e to the negative kt. Notice I have not put any numbers in yet, but because this relationship, the definition of a half-life is when my amount is half of what I started with, the amount that I started with goes away. In fact, the dirty secret about exponentials is they are percentage generators. When I have a negative exponential and it's decaying, the largest this number will be for positive t is 1. And it works its way down to 0. And so everything in the middle is a percent of my original value. And so when I'm saying half-life, I'm saying, when do I have 50% of my stuff? When do I have 50% of my stuff? Doesn't matter how much stuff I have. The more stuff I have, half of it is still 50% of the stuff I have. All right. Well, I want to get my variables downstairs. So I'll take the natural log of this side, and I'll take the natural log of this side. That's okay to do. Right? Because if the left-hand side is equal to the right-hand side, and I put the left-hand side into the natural log, then I'm putting the right-hand side into the natural log should equal. Okay, that's the joy of equality. That's the mathematical balance of inequality. All right, so I'm going to play a trick with this. This is the same as ln of 2 to the negative 1. Right? 1 over 2 is equal to 2 to the negative 1 from our rules of exponents. These two things cancel each other out. They're inverse functions, so this gives me negative kt. My rules of logarithms, going all the way back up here. Again, these are, you're going to keep coming back to these. These are on the handout sheets that I gave you at the beginning of the year. The rule of logarithms, I have a multiplication so that can come out front. Back down here, there we go. And so this can come out front. That's negative ln2 equals negative kt. The negatives cancel. And ln2 equals kt. Well, k is the thing I don't know. So I'm going to divide both sides by k. And I get t is ln2. Whoops. K is the thing I don't know. Solve for k. K is equal to ln2 over t. And t, in this case, is my half-life, the 5,730 years. And so I have a k equal to ln2 divided by 5,730. This is a number. I can put it into the calculator and I can get a decimal representation of it. And that's what we tend to get for these rates of decays. We tend to get a number for them. LN2s pop up a lot in mathematics because of the idea of decay and growth. And I get 1.21 times 10 to the negative fourth, or 0, let's see. One, two, three, four, yep, right there. My value of k is this. Now notice how my algebra let me focus, the algebra that we have with these new rules lets me focus on the value of k, which was in the exponent before. So my model for carbon half-life now is my amount is equal to the amount I start with times e to the negative 0.123121 times time. And that is carbon. It's half-life. All right. Well, I'm going to mess with you just one more time with the carbon's half-life here. All right. Most of my RadTech students, they would memorize this for half-lives. K equals ln2 divided by the half-life. K equals ln2 divided by the half-life. K equals ln2 divided by the half-life. Because it's easy to remember. All right. You know me. I say it every other class. I can't memorize anything to save myself. So I always remember how to derive things. And this is the derivation of where we get the half-life formula from. But let's use this. And so let's say I start with, where is it here? If I have a bone that has 85% of the carbon-14 in it, when did that bone decay? Now, the thing about carbon-14, if you want a little biological fact, it's in corn. One of the things I do in my physics is we can actually measure when people stop ingesting. The different types of carbon grow in different substances. You ingest them in. Once you ingest them in, it starts radioactively decaying. So you're eating corn. You can determine the ratio of carbon-14 to carbon-12 in corn based off of the type of corn isotopes it has. There's a lot of things we can do looking at the different elements that we find in things. Well, once you die, you're not ingesting any more carbon-14 in. So all it is doing is decaying, leaving carbon-12 and other components behind. So if you have 85% carbon-14, we can figure out how old the bone is. Well, let's use this idea. Is my current amount is equal to 0.85 of my initial amount. All right, that's what 85% would mean. Remember, these exponentials are percentage generators, right? They spit out a number between 0 and 1 that is equivalent of a percentage. So if I know the percentage of stuff I have, well, how old is this bone? So 0.85 a sub naught equals a sub naught e to the negative 0, 0, 0, 1, 2, 1 times t. Well, it's a percentage generator. I don't need to know how much the bone I have because those two parts will cancel out. I need to know when this exponential is going to spit out 85%. Well, my t is in the exponent. I need it to come down. To do that, if I take the natural log of this, my rule of logarithms says, hey, this inverse function of this, right? And the rule we had of inverses, if I composed a function of its inverse, it would spit back out the x. And so it would spit back out this. So when we have something raised to a power and we need the thing in the power, we're going to take the log that corresponds with our base, because these will cancel. And on my right hand side, I'll end up with this, which is nice. I know how to do multiplications. Well, if I take the natural log of the right hand side, what do I have to do to the left hand side? The same thing. Take the natural log of the left hand side. And so I'll solve for t, ln 0.85 divided by negative 0.000121. My calculator. Too many hands here. So ln of 0.85 divided by negative 0.123121. And I get that this is roughly 1,343 years. All right, so I'm going to be wrapping up for today. All right, now I'm going to just overview what we've done. Okay, we have introduced two classes of functions that we're operating on. We're doing operations on them. We're treating them like multiplications and divisions. And there are exponential and our logarithmic functions. They're brand new. There are an infinite amount of them because we can choose as many, the bases can run the range of real numbers. Specifically positive real numbers that aren't 1. Tends to be the things we like to use, but they can run the gambit of real numbers. Positive real numbers. So these bases represent multiple multiplications. That is very, very, very relevant to the world we live in. Things multiply. Again, I'll throw out the biblical quote, go forth and multiply. Population models literally translate into multiple multiplications. The exponential is a great model for population growth, if not from decree in Genesis. Right? Also, systems, because systems of growth tend to work from splittings and copyings, the converse happens. We have logarithmic models, the inverse. We had to invent that inverse from the graph. And, whoops, I made that go really small. And so, and that's too big. There we go. And so inverting these functions and moving forward and backwards in these functions gives us a set of rules that chain them together. And these rules I'm going to highlight up here as I scroll back up to them. All right. And so these rules that move back and forth between logarithms and exponents are going to help us manipulate when we have exponential things. Because our problem is we had no way of getting things out of the exponent. Well, if we look at these rules carefully, the magic sauce here, where these things cancel each other out, get things out of the exponent, and this multiplication rule in logs gets things out of the exponents. And so these kind of become the tools we use for pulling things out of the exponents so that we can get them in a linear or graphical or mathematical system where our familiar calculations come from. Now, our calculators and tables only have a limited amount of bases. And so the first algebraic thing we wanted to observe in this was how we could change our base. And we did it so that we used two different bases. We used the natural log and we used log base 10. And we realized using either base we got the same result with our formula. And that's this here. Okay. And then I went in and specifically looked at some models we did before. We looked at the radioactive decay model and we said, hey, I could tell you how much of stuff I could get plugging in the exponent, but now I can tell you how long it takes. And I also used putting that model into E for the exponent because we're going to find that that happens a lot. I'm going to put E in. And then we also looked at some logarithmic models. So we have the basis for a new set of operations that we can do in algebra. And what we're going to do on our last class is we're going to look at section 5.5, which explores the property of logarithms and the property of exponents in 5.3. And we're going to do algebra with them. We're going to solve exponential equations and logarithmic equations, which is also in 5.7. It's going to be most of the first half of the class is the algebra with it. The last half of the class is we're going to look at some more complex models that come out of here. We're going to look at the logistic function, which is what happens when you have population growth met with population decay. I was doing some work for my ordinary differential equations class, which is coming up in the spring, and I was looking at logistic growth models. And they're where exponentials fall out of these calculus problems. And the answers that you get based off of certain starting conditions aren't calculus anymore. They're exponentials and logarithms. And logistic models have the fish breed at a certain rate, and so they're growing in the lake, but the lake only has so much food for them. So once so many fish get into the water, they start starving, and so they die off. And there's this competition between growth and death rates where they reach a level population that is a sustainable population. Which, in the real world, it fluctuates because the conditions of growth and decay are not static. And so we're going to look at those models. But to do that, we're going to have to explore the algebra that comes out of it. And so I've introduced you to these new class of functions. I've shown you some of their utilities. We've done a little bit of the algebra with them. Practice the homework problems. Send me questions. Emily, I will send you an email now that I got my answer back. I'll start composing that here. You're going to be in a good place. Eric, if you need anything specific on this 50 through 55, I went through and did them all again, and I looked at the one that you had. I actually had to hit that page like 5 times to get, I think it was number 50, to give me a bad answer, but I was able to pull that one out. But if you do have any problems with those, continue to let me know. All right, have a wonderful evening. I really miss hanging with you guys. Right now I would have been looking out the window off at the road and watching the traffic down by Haywood, right? Or Harwood. Harwood, the hospital. Oh well. Have a good evening, all right? Hope to see you all soon.